Hello, this is Mr. Gilmore with the 9.6 applications lesson. Now, this applications lesson is going to be going over several of the definitions and theorems that we've encountered in this first part of our chapter. So, we're going to encounter several of the information that we've already seen as review in the beginning of this lesson, and then we'll dive into actually using those theorems as far as application goes in determining whether we can find the measure of a missing angle or the measure of a missing arc. So let's just go through several pieces of information to review. Let's talk about the central angle measure. Now, you've seen all this information. You're not going to need to write this down. So I'm going to go through these next several slides pretty quickly. So the central angle measure, remember that by definition, that when we're given a central angle, that angle has measure. And what we're also doing is we're saying that the measure of the arc that it cuts also has that same measure. So the measure of arc AB is equal to the measure of that central angle, angle ACB. Now, we juxtapose that against then the inscribed angle theorem, which says that the measure of our inscribed angle is actually half the measure of the arc it cuts. In our diagram below, we have the measure of angle BAC, which is actually equal to half the measure of arc BC. We've also got corollaries of the inscribed angle theorem. So this one says that if you've got two inscribed angles that cut the same arc, then those two inscribed angles must be equal in measure. So in other words, in this diagram, angle B and angle D actually cut the same arc, arc AC, which means you can claim angle B and angle D must be equal to each other. You can also claim angle C and angle A are equal to each other because they also cut the same arc. They both cut arc BD. Another corollary of the inscribed angle theorem is one where parallel chords cut equal arcs, which means if you've got parallel chords BC and DA, that means you can claim that this arc measure of BD is equal to this arc measure AC. And we'll see some use of that as well in some of our application problems. We have Thales' theorem, which Thales' theorem we saw in the last lesson 9.5, where if you inscribe a triangle such that one of the sides is a diameter, that means you're working with a right triangle. We actually prove that angle CBD or angle B there is a 90-degree angle. Now, the converse of Thales is also true. If you inscribe yourselves a right triangle, that means the side of your triangle must then be a diameter. So CD is going to be a diameter of the circle. The inscribed quadrilateral theorem, this is actually one that comes in handy quite often, that the opposite angles in a quadrilateral are what we call supplementary, which means there's sum of those measures add up to 180 degrees. Now, in this diagram below, we can claim that angle B and angle D are supplementary, and we can also claim that angle C and angle E are supplementary, that opposite angles will in fact add up to 180 degrees. We also took a look at inscribing special types of quadrilaterals, so that in the inscribed parallelogram, where if you inscribe a parallelogram, it turns into a rectangle. So BCDE, we actually know the measures of all four of those angles there. We can prove that they are actually right angles. The inscribed rhombus. If you inscribe a rhombus, you then know that that inscribed diagram there we find to be also a square, because inscribed rhombuses are also parallelograms, and if we inscribe a parallelogram, it's a rhombus, which then makes that BCDE a square. We also have our inscribed trapezoid, where if we inscribe a trapezoid, it turns out to be an isosceles trapezoid. With the isosceles trapezoid, we know that the legs are equal to what we're saying, that BE and CD are equal in measure. And also we know that the base angles then of the isosceles trapezoid, which is a property we proved way back in chapter 6, that the base angles of the isosceles trapezoid are also equal in measure. Now what we're going to do on the last several slides is just look through several examples where I'm going to give you a diagram and ask you to find a missing either angle measure or missing measure of an arc. So in the diagram, we're given that this is a parallelogram that's inscribed BCDE. I want you to find the measure of angle CBE. Well, we know if it's an inscribed parallelogram, that means by our inscribed parallelogram theorem, it must be a rectangle, which means we can immediately claim the measure of our angle CBE, because all four angles in a rectangle must be a right angle. So the measure of our angle CBE is 90 degrees. And there we have it, using our inscribed parallelogram theorem to help us find a missing angle measure. Let's do another example. If we're given that the arc measure of BC is 140 degrees, so this arc measures 140 degrees, find the measure of angle BAC. Well, angle BAC, do a little bit of analysis. You come to the conclusion, that's a central angle. And the measure of a central angle is actually equal to the measure of the arc that it cuts. So the measure of BAC is actually equal to 140 degrees because it's cutting that arc, which is also 140 degrees. Now, don't confuse this with the inscribed angle theorem. The inscribed angle is where the measure of the inscribed angle is half the measure of the arc it cuts. But with central angles, they are equal to the measure of the arc they cut. So now let's do an example where we're actually working with a central angle and an inscribed angle. In the diagram, we have angle BAC is given to us as a right angle. We're trying to find the measure of angle BDC. Now, if you take a look, both of those angles are cutting the same arc. That BAC is cutting the arc BC, and that the BDC, angle BDC, is also cutting the same arc. The difference between these two angles, BAC and BDC, is one is a central angle and the other is an inscribed angle. If we know that BAC is a central angle and it measures 90, that means the measure of the arc it is cutting also measures 90 degrees. And because of that, we can then find out the measure of angle BDC, because the measure of angle BDC is actually going to be half the measure of the arc it's cutting. That's an inscribed angle, and inscribed angles are half, which means we come to the conclusion that our angle measure there for angle BDC is 45 degrees. We look then at our next example. This one's a little bit more algebraically involved. We're given this circle A with our triangle BDC. We're given that arc DC is twice the measure of arc BD. Find the measure of angle BDC and angle CBD. Well, let's take a look at our arcs first. If you notice, DC and BD are actually related to each other in a certain way. First of all, we know that's given that that DC is twice of arc BD. But there's another thing. If I were to add the two measures of these arcs together, what would they equal? If you see that BC is a diameter, that means BD and DC add up to 180 degrees. So if I were to call BD x degrees, that means DC must be 2x. And we know the sum of those two must add up to that complete semicircle, which semicircles measure 180 degrees. We can then use this to solve for our missing x measure, which we come to the conclusion that x is really 60 degrees. So in other words, BD measures 60 degrees and DC measures 120 degrees because it's twice that of our arc BD. Now, why is that helpful? Because angle BDC, well, actually, let's do angle CBD, this angle right here, angle CBD. It's cutting out the arc from point D to point C. And if we know the measure of that arc, we know the measure of that inscribed angle, our angle CBD. So the measure of our angle CBD is actually equal to half of the measure of the arc it's cutting. Well, the arc it's cutting is 120 degrees, which means the measure of that missing angle 60 degrees. There's one of our missing angles. The other is this angle BDC. If we take a look at angle BDC, we see that it actually is an inscribed angle. If we see that, that cuts a semicircle, right? That's a semicircle. We have Thales' theorem to thank because that inscribed triangle has a side as a diameter. And what Thales' theorem says that if you've got a triangle that has a side as a diameter, then you know that triangle to be a right triangle. So the measure of angle D has to be 90 degrees because it's cutting that semicircle, and half of semicircle is 90 degrees. So there we have it. We found the two missing angle measures using the information given for us. Let's take a look at our next example. Now, in this next example, we're going to be given side measures of this triangle, and we actually can find a missing measure of this. So we're given in the diagram that the length of BD is a length of 6, and the length of DC is a length of 8. I want you to find the length of BC, this entire length of our triangle, the side of our triangle there. Well, recall that Thales' theorem again. We can then claim that triangle BDC is right thanks to Thales' theorem. Okay, Thales says that if we inscribe a right triangle such that, if we describe a triangle such that one of the sides is diameter, that triangle must be a right triangle. In other words, angle D is a right angle. Now, I'm asking you to find a missing side of a right triangle, and I gave you two sides. What is our theorem that actually we can tap into? The Pythagorean theorem, PT. So we're doing 6 squared plus 8 squared. We're looking for the length of BC. So I'll say is equal to BC squared. We have 36 plus 64 is equal to BC squared. 36 and 64 equal 100. I'm going to flip my equation around when I take the square root here. So BC is then equal to a length of 10. And that's again thanks to two theorems, the Thales theorem, which actually shows that it must be a right triangle, and our Pythagorean theorem, which means we can solve for a missing side measure of that right triangle. On to our last example, which is another little bit of a tricky one. If I have a diagram where I've inscribed a regular polygon, we can actually find the relationship of the sides of that regular polygon with what we call with the radius of the circle. If you notice that AD is a radius, and what we're given is the length of one of the sides of our triangle BC. We can actually find the length of AD using what we know about our circle relationships of the regular polygons that we have. So first off, we have this regular polygon BCD, which is actually cutting our circle into 3 arcs of equal measure. So this arc, or basically we're taking 360, dividing it by 3, which means each arc is cut into 120 degrees. So this arc is 120, this arc is 120, this arc is 120. What we're going to do is find the missing length of AD. Now here's what we're going to do. We're actually going to construct another radius from point A that goes through and actually intersects our chord there, CD, such that it's going to be perpendicular. Now, when we do that, we learn something about radii or diameters that are cutting through a chord and making perpendicular. It actually cuts that chord in half, which means if we know that all 6 sides there measure, sorry, all 3 sides there measure 6, we can then say that each of those 2 halves must measure 3. Now, why is that important? Because there's going to be something special about this triangle. I'm going to call that point M. This triangle ADM. That's what we're going to look at right next, or right now, when we zoom in on that little portion of our triangle, ADM. We know we have a side of that triangle. MD must be a length of 3, but we actually can determine an angle measure, because what happens is when we connect that radius and it intersects our arc here, it actually cuts that arc in half as well, which means the arc measure here is 60 degrees. Now, why is that important? Because we have a central angle measure here, angle DAM, which is also then 60 degrees. And what are we dealing with? We're dealing with a 30, 60, 90 right triangle. So I'm going to zoom in on that triangle. So I've zoomed in on this triangle that's formed in our diagram. We had point A, we have point D, we have point M, and we've got that right angle. We just proved that that's 60 degrees because the central angle, and we've also got this side length to be a length of 3. In a 30, 60, 90, we can actually then work to find out what the missing measure of the short leg is, and then lead us to figure out the missing measure of our hypotenuse, which AD is the length we're looking for. So to go backward from our long leg to our short leg, we are going to divide by root 3. When I do that, I'm going to save ourselves some time here. I'm really doing 3 divided by root 3. I'm going to rationalize that, which means I end up getting just root 3 is the length of our short leg. So this short leg, root 3. Now to go from our short leg to our long leg, remember that you have to double that, just multiply by 2. So we take our short leg, x, root 3, and double it, which then you're just doing 2 times root 3, and there is the length of our hypotenuse, which is AD. So we go back to our original diagram and say, hey, we're looking for the length of AD. We found it. The length of our AD there is 2 times the square root of 3. And we can relate that using the information we've studied with our circles and actually tying that into some old relationships with our 30, 60, 90 right triangle. So please be sure to hop over and take a look at that worksheet 9.6. If you do have any questions about the application section of our chapter here, please don't hesitate to email me. With that, be good and do good.